I guess we can move on to stochastic gradient descent. But now we are getting a little bit more ambitious. We know that training a neural network on ImageNet is going to take you around 1 week on a single GPU. Now we want to get more ambitious. If you have enough compute, for instance, if you're working in a large company like Google, Amazon, or Facebook, you have enough GPUs in front of you, can you actually train much faster, maybe in less than 1 hour? So that's the idea. And then by training, you're going to use a stochastic gradient descent. That's what we're going to use. You usually have a loss function. It's going to be parameterized by the parameters of your neural network. You're going to divide by the size of your data set. So X is your entire data set. You're sampling data from your entire data set. And then this is per example loss, which is your cross-entropy loss in the case of ImageNet and classification. And the parameters of your neural network are going to end up being the parameters of your loss function in the end. Now you're doing the summation over your entire data. That's your loss function. These are the weights and biases. X is your labeled training set. So it's both images and labels. And then this could be your cross-entropy plus a regularization term, like L2 penalty. You don't want your weights to become too big. You want to regularize them. And then in practice, you are not going to do your summation over your entire data. You're going to take a mini batch of your data, and that mini batch is going to give you an approximation to the true gradient. And then you're going to do steps in that direction. And that's your step size. That's your learning rate. And that's a stochastic gradient descent. And we covered it a long time ago in the course. B is a mini batch, and you're sampling it from your entire data. And usually your mini batch is going to have a smaller size compared to your entire data set. Now you have multiple GPUs in front of you. And by a server, I mean a computer, it could have 2 GPUs in it. It could have 4 GPUs in it. It could have 8 GPUs in it in the case of a DGX1 machine, where it could have 16 GPUs in it. That's your K. N is how many samples you can process per single GPU. So that's a mini batch per GPU. For instance, if you have a DGX1 machine, it's going to have 8 GPUs. Let's say you're processing 32 images per each GPU. Your batch size is going to be K times N, which is end up being 256. Now we're going to move towards the case where you have multiple servers. Not only you have a single computer, you have multiple computers in front of you or in your network, and you want to use all of them. And you want to do data parallelism. You want each GPU to process 32 different images, each server to process 256 images, and then you have multiple servers, maybe 10 of them. And you choose a learning rate. You choose a learning rate for this baseline. And this you found it through trial and error on your validation data. And let's say this is the optimal value. This is 0.1 for your learning rate. The question is, what's going to happen to your learning rate if you have twice more servers or 5 times more servers? What should be your learning rate? So that's the question we want to answer. And the bigger your learning rate, the faster you're going to learn. And then you're going to learn in perhaps less than 1 hour. So that's the idea. You want to determine your learning rates for large mini batches. So you are increasing the size of your mini batch. And you are doing data parallelism because you have multiple servers in front of you. And let's reformulate this 0.1 a little bit. In the case where beta, or the size of your mini batch, is 256, that number is going to cancel with 256 here, and then you're going to get 0.1. So what do you think should be the learning rate if I increase K by 2 rather than it being 8, it being 16? So I want you to brainstorm a little bit. Let's make a hypothesis. Any ideas? Okay, that's a good guess. So you are saying it should be 0.2, but why is that? There is this observation, and we are going to go through a little bit of math, trying to discuss this makes sense. And that's the rule. Where mini batch size is doubled, maybe it's multiplied by K, you need to double your learning rate. So you need to linearly scale it by the same constant. And why is that? Let's say you have some mini batches. Let's say you have k mini batches of your data. You can process them sequentially, process the first mini batch first, the second mini batch second, on a single GPU. So you first process 32 data points, then you process the next 32 data points, and then you move on. Or you can increase the size of your mini batch to be k times n, k times bigger, and process it at once for a single step of your gradient descent. And let's study those two cases. One is iterative, the other one is processing the entire k times n data points at once. What's going to happen? And let's see what is going to happen. You're going to do k iterations of a stochastic gradient descent. You choose a learning rate on a single GPU, and then you choose your mini batch size, which is n on your single GPU. And then you're taking multiple steps of a stochastic gradient. The first step is exactly this one. The second step, you're going to see your second mini batch, and then you're going to update your W to be your weights t plus 2 at times t plus 2 is your WT minus your learning rate. This is the size of your mini batch, which is 1 over n. And then you're doing a summation over your first mini batch, second mini batch. And then these gradients, you're evaluating them at different points. The first one, you're evaluating it at W0, W times WT plus 0. The next one, you're evaluating at WT plus 1, because it's the next step in your iteration. So you're just calling this guy twice, or you can call this guy k times, and that's going to give you WT plus k. These are your parameters. After taking k steps of stochastic gradient descent, what happens if you have a very large batch and you take only one step? You're going to go to the next step. That's going to, let's call that W hat. You're at WT. You have to choose a learning rate. Let it be flexible for now. Then the size of your mini batch is 1 over k times n. And then you're doing a summation over your gradients. But then this gradient of your loss is at the previous time, at the parameters at the previous iteration. So I guess this should answer the question on the chat. So this new mini batch, and by new mini batch, you mean the larger one, is a bigger mini batch. And then it's across all of your servers. Yeah. And k could be, here we are adjusting k. It could be 8, 16, 32, and 1,000, even bigger. Okay, so this should answer your question. But as you can see, these are not equivalent. Can somebody tell me why? Okay, perfect. This is 1 over n. This is 1 over k times n. That's correct. So that's one reason. There is another reason why they are not equivalent. This is WT. This is your learning rate. This is 1 over k times n. These summations match. The gradient of your loss match. This is x. Exactly. So these two don't match. This is evaluated at WT. The other one is at WT plus 1, WT plus 2, WT plus 3. And because you're doing optimization, there is no guarantee that these two are equal. So they're not equal. But because you're doing optimization, you're taking tiny steps. These are going to be very close. They're not going to be identical, but they're going to be very close, especially during the end of the training, during the end of the optimization. So perhaps later on in the optimization, you can assume these are equal or very close to each other to some first order approximations. And then we can go back to your first point. You choose eta hat, the new learning rate for the bigger batch, to be k times bigger than the learning rate for the smaller mini batch. And these two formulas are going to match, the one above and the one below, because this is going to be k times eta, and then those two k's are going to cancel, and these two are going to end up being equivalent. And in that case, you can say that these are approximately close to each other. And this is why, as soon as you double your mini batch size, you're going to need to double your learning rate. If you triple your mini batch size, you're going to have to multiply your learning rate by 3, etc. Okay, and that is where the linear scaling rule is coming from. So there is some math behind it. But this assumption here, these two being close to each other, it only holds when you're later on in your training. Initially, things are changing rapidly from one iteration to the next iteration. So this is not a good assumption initially. So initially, you're going to set lambda hat. This is a ad hoc method. You're going to set it to be equal to lambda, to the learning rate for the smaller mini-batch, because you're not going to lose much. You're slowing down your convergence from one iteration to the next one. You're slowing it down a little bit. You're learning slower. So you're not going to lose much. But then gradually, after seeing your entire data set for 5 epochs, you're going to gradually build it up until you reach the correct linear scaling rule. So you're going to have a learning rate schedule. It starts from lambda, it grows up, and then from there on, it's going to be k times your learning rate. How does it work? In theory, we know there is some justification. In practice, it is working like a charm. It is beautiful. If you have 2 GPUs, your mini batch size is going to be 64. And then you keep increasing your number of GPUs. And at the same time, your mini batch size is increasing. And up until 8,000 to be the size of your mini batch, you are processing 8,000 images at a time compared to 32, compared to 64. You're basically having the same validation error. And then you're learning much faster. But at some point, the theory makes sense. But at some points, these errors are going to end up being too big because your learning rate is too big. That at some point, this linear scaling rule breaks. So maybe you need to lower your learning rate after a while. Okay, any questions so far? So there is a question, how do the separate servers combine their learned weight adjustment each step? So each server is you can correspond it to a mini batch. Each server is gonna compute its own gradients of your loss. So you're gonna have a copy of your model on multiple GPUs. And each one is just seeing different data, and they can take the gradient of their loss with respect to the parameters according to the mini batch that they saw. But once the gradients are computed on that particular machine, on GPU 1, then they're gonna give all of those gradients. These are gonna be clients. They're gonna send that to a server, and on that server, you're gonna do this addition. So these summations are done in parallel. These gradient computations are done in parallel on multiple GPUs. They're computed, and then you're just passing the gradients back to a server that does the addition here. And once you do the addition, you can update your parameters. Same thing here, it's the same thing. There is another question, do they do averaging or do they go through an epoch separately? No. Initially, you have your entire ImageNet in front of you. It's 1 million data. You're going to first shuffle it, and then you're going to sample, in this case, 8,000 images. And those 8,000 images, you're going to divide them into K GPUs. And then you're going to give that data to your clients, which are actually multiple computers. They're going to do the gradient computation on their own mini batch of 32 images. And then they're going to pass back to you their gradients. And then you do the addition. There's another question. Can you explain again why the both losses are not the same initially? Yeah, sure. So initially, actually, we were working under the assumption that from one iteration to the next iteration, your W's don't change that much. So at iteration 1, you have W0. Actually, it's better to start with WT. At time t, you have WT. At time t plus 1, you have WT plus 1. These are close to each other because learning rate is small anyways. It means that as soon as you write down your Taylor expansion here, ignore the higher order terms because WT plus 1 was close to WT. The gradients are going to be close to each other as well. So that's a good assumption. But once you're in the middle of your training, maybe after 5 epochs, but initially, this is not a good assumption that WT plus 1 is similar to WT, because initially, if you look at your loss, it goes down rapidly. What does it mean? It means that your W's are changing rapidly. So initially, you're going to learn really fast. Okay, so this assumption doesn't hold. That's why you're going to build up. You're going to start slow up until you reach k times eta after 5 epochs, and then you're gonna work with this assumption, which is a good assumption down in the road when you're training. Okay, there is another question. Is this applicable when you aren't using vanilla stochastic gradient descent? That's a great question. And actually, you can imagine if scaling up to multiple GPUs for a simple stochastic gradient descent took you some thinking, it wasn't trivial, then it's going to be a little bit harder when you add momentum to your stochastic gradient descent, when you add some regularization on your parameters. So it's not like you increase the size of your data, your mini-batch, and everything is going to work magically. So you need to be careful a little bit. Go through the math, make sure they are equivalent, and then you can then scale add-on or add a grad or add momentum. Okay, but these are really good questions. And I know that the paper considers momentum as well. So there are some pitfalls that you have to be careful about. It's not a trivial task. I have more GPUs. I'm going to do data parallelism, and then I'm going to be happy. And then I'm going to be able to train in less than 1 hour. No, you have to be careful. Okay, any other questions? One other pitfall is batch normalization. How are you going to do batch normalization? Is it trivial? I'm going to do a batch normalization on my entire data. Am I going to do batch normalization on k times n? Or am I going to do batch normalization per each GPU? It turns out that no, it's not trivial. Not only for the sake of reducing computation, you want to compute your mini batches per each GPU, your mini batch statistics per each GPU, which is basically the size of n. You don't want to use k times n because then your GPUs need to communicate with each other. You need to pass some data from one GPU to the next one. So for the sake of reducing computation and communication, you're going to stick to per GPU batches or batch normalization. There is also some underlying math that tells you that these are not equivalent. And what is that? Let's go through batch normalization. We know that for batch normalization, this loss that you're writing here per each example depends on the batch. It depends on the mean and the standard deviation of the batch, of your mini batch. And then you're sampling multiple batches from your data set or mini batches from your data set. Okay, xn is your data set, or it's a set of mini batches of your data set. And then you're going to do the averaging. You were doing it here. That's the averaging over multiple batches. It's the same formula here. Over there, you had gradient. Here you have just your batches. And then per each GPU, you're going to have n data points. And then you're going to do a summation of individual images on the images in that GPU, in that particular GPU. Okay, so far so good. That's the capital L in terms of notation. That's the little l. It depends on your batch, etc. And as I mentioned, xn is just subsets of x, subsets of mini batches of x. What is the observation? This loss is going to change as you change your n, your mini batch. You have two choices here. The statistics that you're computing here, your mini batch, could have a size of k times n, or it could have a size of n. This is under the assumption that this is having a size of n. If it has a size of k times n, your mini batch is going to have a bigger size, you're going to have a different mean, you're going to have a different standard deviation, and then your mini batch is going to be, your batch normalization is going to be different. So your losses are going to be different. So this loss is batch dependent. To do it properly, you need to have n examples per each GPU, and then your mini batch is computed based on those n examples, those statistics, the mean and the variance. So mathematically, they are not equivalent. And as you mentioned, there are other pitfalls and subtleties when you're doing distributed optimization. And for that, I want you to take a look at the paper. That's actually the title of the chapter in the paper that you can take a look at. These are minor details. They are not as big as batch normalization or stochastic gradient descent, but there are still some other minor details, like momentum. How do you add momentum? How do you scale your cross-entropy loss? Is this equivalent to scaling your learning rate? yes or no? How do you normalize per worker loss? Do you need to normalize it by k times n, or do you divide it by n? And do you use a single random shuffling of your entire data set per each epoch, or each GPU is going to sample independently from your data? So these are going to be different when you scale things up, and you have to be careful. I think it's a good time to stop and ask questions. And for those of you who want to leave, you can leave. I'll be around.
Thank you.